Hi guys, today I would like to talk about the exponential of matrices. Uh, of matrices and uh, and also a little bit about the uh, exponential form of the complex number e to the I x. So why what does this mean and how it's related to sinus and cosinus of x. And I'll try to do this step by step as usual. Uh, Hopefully, I'm not doing too many mistakes because last time I did one big mistake, which was e to the I pi over 2. I said it was equal to 1, which is clearly wrong because e to the I pi over 2 is equal to I. 1 is only e to the I pi is equal to minus 1 actually. Yes, sorry, think so. No, actually it's minus 1 is correct, minus 1, because uh, and I will tell you why this is the case in, uh, in in this video. So I'm sorry for the hiccup there, but I didn't prepare much and I was just going a bit with memory, and sometimes it's not a good place. Okay, so uh, let's start with something. Uh, so let's start with something to just to give you an idea. Okay, so we know from our video on exponential functions that e to the e to the x, sorry, can be written as a sum of infinitely many terms, where x is exponentiated to the n, and then there is n factorial. I'm not going to go over, and this is n. I'm not going to go over this again. I will make a video on this kind, the exponent, so the sum representation of functions, but dedicated video for that. But for the moment, we use this as a definition that we use to exactly define e to the x, and in fact we started with the definition of e to the 1, which was e, the number, the irrational number, which was exactly where you replace 1 over n factorial of n from 1 to infinity. Okay, so this is just a recap to refresh our minds and not fixate too much on the summation to infinity, but let's keep it. We can work with, if you are more comfortable, we can say that e to the x is roughly, not exactly, but roughly equal to the sum over n equal to big N, a large n, whatever this is, for n much, 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 much bigger than 1. I don't know. Pick 10,000, pick a million, pick 2 billions, whatever. I mean, a huge number. I mean, I think 100 is already enough to have a decent approximation. But since E has an infinite representation in decimal digits, we can go as high as we want. Okay, so, and this would be a finite sum. So we know how to deal with finite sum. So let's see if we can derive the exponential form of e to the I of e to the ix instead. Okay, so e to the ix, at the moment we don't want to do the formal derivation of this, which would be to extend the function from the real numbers to the complex numbers, which can be tricky, depends on the function. There are subtleties. It's a huge mathematical field of study. It has been studied thoroughly, and it's not very easy to compress in a few slides. What I will do, I will just give a pragmatic point of view, and I will basically try to make sense of the, let's say roughly, and then we'll go to infinity, to the sum of n from 1 to big N, we said, okay? And now instead of x here, we put ix, equal to the n divided by n. First, I want to let you know that I'm not cheating here, because we already know that e times a real number a, is equal to ia without the dot, so it's a coefficient in front of the number. It's just like when you multiply 2 times a, you get 2 twice a, or whatever number. I, we already said that is this special number on the vertical axis in the complex domain, and it behaves like a coefficient in front of any real number. Also, we need to remember one simple thing, that is a to the n is equal to the a. I'm sorry if I'm being pedantic, but for those who n times. So a to the n is a way of represent the multiplication. So with these two combine, when these two, let's say 1 and 2, these 2 points combine, we can make sense of this this expression here, right? Because let's say e to the x, we got it. E to the x to the n would be e to the x times I to the x, I to the x, I to the x, and this is n times. We have no problem with that, because we know how to multiply to complex number. I will give you the recap here. So I erase the definition of e, which is well, we already did a video on that, so that's enough. And then I will recap multiplication of two complex number. So if we have a plus ib times c plus id, these are two complex numbers, and we know that this is ac minus bd plus I AB plus AD plus CB. Right, the cross terms, the one that are they're called cross terms. Anyway, so we did this times this, this times this, and then, as I said, we did the cross terms, which are this times this and this times this, because they cross. Okay, so now for our special case, which is ix, and we can call it, we remember that we can do this, we can add a 0 as a real number, because every imaginary number can be thought as a complex number with a real part of 0, which makes sense because we put it in the graph this way, right? Here the real number and here I real numbers, and this is a complex number. So when this is 0, we get this imaginary line here, which all have 0 component in the real part, which is this part here. So if we explicitly do, I mean, I'm being over pedantic, but just to tell you that you can always, if you don't remember that I times IA times IA can be written like minus a squared, you can always go back to this definition, do this instead, and you will see that these terms times this will be 0, this term times this will be 0, and then we get this term times this will be 0, and then we only get these terms times these terms, which is I times x squared, which is minus 1x squared.